Okay, so what I want to show you in this video is the Kronig-Penny solution in Python. So a little refresher, the Kronig-Penny solution deals with the 1D wave function. So we solve Schrodinger's equation for a one-dimensional crystal lattice. Okay, so this is, for example, a semiconductor. So if we have repeating crystal lattice of atoms, each one of these repeating unit cells is identical, and we have no boundary conditions. It's an infinitely long crystal. Here's what our potential would look like. Okay, so we have a potential landscape where around each atom there's a deep potential well due to the Coulombic force pulling the electron towards a positively charged nucleus. Now, the Kronig-Penny model, as we show here, is if we assume a square potential for the nucleus pulling the electron. Okay, so as the electron is traveling across this lattice, it sees a periodic potential that we approximate with a square function. And we do that so we can get an analytical solution. So the important parts here are that the repeating unit cell is some distance A plus B. This is the lattice, where A is the depth of the well, the width of the well, and B is the width of the spacing in between the potential wells. And U naught is our potential energy depth for the well. Okay, so this is U naught is how high the potential well comes up. Now, what we've done in a separate discussion is solve the wave function, Schrodinger's equation, using Bloch's theorem, which is the periodic potential for boundary conditions. And this is what we get. Okay, so we take this equation and we have this as the solution. Okay, and we're defining two terms, alpha naught and epsilon. So epsilon is going to be the energy relative to the potential height. So for example, if the potential height is U naught, this is going to be epsilon equals 1. And for energies greater than this, epsilon is greater than 1. And for energies less than that, epsilon is less than 1. Okay, so this is why we have two solutions. We have a solution for epsilon greater than 1 and a solution for epsilon less than, I'm sorry, backwards. This one's greater than 1. The other one's less than 1. And there's not a nice clean analytical solution. So what you have to do is plot the left-hand side, which is a function of only energy, and the right-hand side, which is a function of K, to reconstruct our E-k diagram for a semiconductor. So we don't know what the band diagram looks like, the energy momentum diagram looks like for Kronig-Penny solution. Okay, so let's take a look then in Python about what this looks like. So here we've got a solution which I'll load for you, which is essentially solves the Kronig-Penny model. Okay, so the Kronig-Penny model will take some inputs. So the solution to this model takes inputs of the lattice spacing and the energy, and then what epsilon range you want to solve for. And what it does here is it inputs some constants, and it solves for the right-hand side of this solution. So we can make a plot of this equation that I just showed you. And then we've got another function here, which is going to be able to reconstruct the energy bands. So solve for values where this overlaps. Okay, so I'll go through it and show you. So this function is solved as kp underscore solution. Okay, so if you save this file, download it and save it in a directory, then what you can do is you can open a new Python script in that same directory. Okay, doesn't matter what you call this one, and we're going to import the other one. Okay, so what you can do is you can say from and then kp solution. So this is from that script I just solved. The kp solution is the name of the other file. Basically, we're going to import that file. We're going to specifically import different functions for it. So kpm solution is what we want to import. Okay, so this is going to be, we're going to import this function. And so let's plot it. Okay, so the first thing we have is some system variables. Okay, so let's say we need to define our system. So if we look at this, we want to input the lattice spacing in angstroms the potential energy in EV, and then the total desired range for the output in epsilon. Okay, so let's say our lattice spacing is 2.7 angstroms for both A and B, so the both spacing. This is similar to maybe a hydrogen atom. Let's say our potential energy is going to be 5. Let's put our units here. So this is going to be in angstroms. This will be in angstroms, and this is going to be in EV. And we want to have an epsilon range, which is we'll say for now 6. We'll go to 6. This is dimensionless. Okay, so now you want to evaluate your function. So this KP solution, what it does is it outputs two things. It outputs the epsilon list and then the function evaluated at epsilon. Okay, so essentially we're looking at the left-hand side of that equation. And so let's say the epsilon list and then the function evaluated at those epsilons, it's just arbitrary function, is going to equal KPM solution. And as inputs, it takes A, B, U naught, and epsilon range. Okay, so now we can output our values. And now we also can take this. So let's look at this. Let's take a plot. Okay, so let's plot Kronig-Penny solution. So the first thing we're doing is say plot figure, and then let's call this figure 1, and we want a nice DPI. We'll say 120, and then we're going to say we're going to make a title. The plot title we'll call the Kronig-Penny solution, and then we're going to have an X label. And so the X label will be, now here we can, we're going to plot epsilon. So this is basically the energy versus the function evaluated at epsilon. So we can use some math text scripts in matplotlib. I've already imported matplotlib here and numpy. So how you can do this is you can put a, put your quotes to put a string, and then you can put this $ to indicate that we're using this math script. And we're going to say the X label is going to be /epsilon, okay? And then our plot Y label is going to be the function evaluated at epsilon, okay? So we can do the same thing /epsilon, and then you have to put a $ to close out each one of these math tech descriptions. Okay, so we have our labels. And let's make the plot. Okay, so we'll say plot, and the X values are going to be the epsilon list, and the Y values are going to be the function evaluated epsilon. Okay, and then we're going to put a label for this. We're going to say this is the left-hand side, so you're clear this is the left-hand side of this Kronig-Penny solution. And we can plot this here. Look at our plot, and this is what you see. So this is the Kronig-Penny solution. So this is what's plotted on the left-hand side. Now, if we want to look at how this function gives us energy bands, we need to look at the appropriate K values. So these are the epsilon values which are possible. Those are the left-hand side of that equation. And now we can plot the K values to plot for the right-hand side. Okay, so that equation I showed, you can go back. It is cosine of K, A plus B on the right-hand side. So basically, this is going to oscillate between 1 and -1, okay? So let's plot this to make it clear. We'll say there's some K list, which is going to be some array. We'll say numpy, linear space between 0, and let's say we want to go between 0 and 6, because that's where this epsilon range goes up. Or we want to just plot it up to epsilon range. We go from 0 to epsilon range, and we need 10 points. And essentially, this is our list, but we're going to make a minimum. So we'll basically take this, and we'll say the minimum value for K is going to be -1. So this is going to equal K list. I'll just say times 0 plus 1, or say -1. And this is just a real easy way to define a list. Or you can do np.full. You can define a function already at a specific value. But I can just take K list times 0 plus 1. Okay, so this is going to be the min and max. So let's add these to the plot. So say plot, and we want to put k-list, and then k-list min. So this is going to plot the -1, and then we'll do plot k-list and k-list max. And oh, I have a little typo here. Okay, and now we can see that this is going to be where the k values are valid, because k on the right hand side oscillates between -1 and 1. Okay, so to make this clear, you can also change the plot style. So we'll do line style equals dashed, and we can say the color is gray, and then we want to label this one. So we'll say label as the right hand side. So let's make these both gray dashed lines on here, and we're going to restrict our axis to say plot, and then we want the y limits, just we'll say between -5 and 5, and then we'll add a legend, and we can plot this again, and this is what you see. Okay, so the blue line is the left-hand side of the Kronig-Penny solution. The dashed gray line is the right-hand side of the Kronig-Penny solution, meaning where the left-hand side is in between these two bounds means it equals the right-hand side. So cosine is going to oscillate between these two bounds. This is going to be -1 to 1. Okay, well, actually 0 to -1 and then back. So it's going to be moving back and forth. So you can look at the solution. This is more how to program it in Python than how to understand the solution. But clearly there's different regions, and these are the energy bands. Okay, so there's a region here, there's a region here, there's a region here, where we can have valid k values and epsilon or energy values. So from this, we can reconstruct an E-k diagram. Okay, so what we're going to do now, and that's exactly what this does. E band Kp basically will feed it this epsilon solution, and it's automatically going to reconstruct an energy band by looking at valid epsilon values for k, the cosine of k, a plus b oscillating between -1 and 1. Okay, so essentially it's going to reconstruct this. So let's take a look. Let's have it reconstructed. So we'll come up to the top now, and we'll import this other function, and it's called eband kp. Okay, so we want to import, and you can just put a comma, and you can import two functions from here, eband kp. And now we need to call it. Okay, so the inputs to the energy band are going to be the epsilon list and the evaluated epsilon list, and it's going to output energy band data. Okay, so we can just say k is going to be the one, so the output is going to be k and epsilon. So this is our E-k diagram. So we'll say k and epsilon are the two outputs, equals this function. So it's going to be E band kp, and the inputs for this are the epsilon list from the previous line and the function evaluated at epsilon from the previous line. So here's our values. So now we also want to plot this. Okay, we'll call this plot figure 2, and we'll also do DPI 120, and we're going to make a plot title, and we'll call this one the Kronig-Penny energy bands, and we'll make a X label, which is, now this is an interesting one, how you can use these math texts to make scripts, mathematical equations. Okay, so for this you can do an R and then the single quotation mark, and this means we're going to go into this math lines. You can look in matplotlib documentation to understand this. But essentially what we're going to do is define a fraction. So we're going to say this is k in the units of, and then we're going to do slash fraction to define a fraction, and then we have two brackets, and in the first bracket, by the way, we need to put a $sign here, and in the first bracket we're going to say it's pi. This is going to be slash pi, and in the bottom it's going to be a plus b. Okay, and then we can close out our $sign, and then we've already ended the quotation. So this is our X label, And then we can do a plot y label, and this is going to be a little more straightforward. So we're going to plot this versus epsilon. Okay. So for this, we'll just do a $ epsilon, and we'll close out this $. So we'll put the epsilon mark. And now what we want to do is look at this solution. Okay. So let's evaluate this and look at what values we have for K and energy. Okay. And essentially, the values we have for K and energy are numpy arrays. Okay. So it's going to output a bunch of lists. So these are the independent energy bands. This is the first energy band, the second energy band, the third, the fourth. So it's going to take and individually reconstruct the energy bands, which correspond to where this would be the first energy band, where the left-hand side is between the right-hand side values of -1 to 1. This would be the second band, the third band, the fourth band. So it's going to collect all these into individual bands. So what we want to do is plot all these individual bands, okay? So we can come here and we'll say for I in range, and we want to plot all the values in the range of the length of K, K being our number of energy bands. So K and epsilon both have our lists of the total energy bands. So we'll say for all the energy bands, what we want to do is we want to plot, and we're going to plot the x values. On the x-axis will be Ki, so it's going to plot Ki, meaning for I equals 1, it'll be, or 0, it'll be the first band, and epsilon I. So it'll plot K versus epsilon for each band independently. Okay. And yeah, this should be good to show a plot here. And this is what you get. Okay. So now we've taken this Kronig-Penny solution where you have these energy bands sliced here. Well, we can't really do anything with this. What we want to do is reconstruct the energy bands. I mean, that's what this does. Okay, so now it's reconstructed the energy bands. So this is our E-k diagram from the Kronig-Penny solution. So this is our first band, our second band, our third band. So for example, if you have electrons filled up in the first two bands, for example, if you had N atoms with each donating 2 electrons, you'd fill up first 2 energy bands. So this would be our conduction band. I'm sorry, our valence band. The orange and the green one would be our valence band, our conduction band. And all you need to do is denote the notations. Okay, so now you can do all sorts of cool things. You can change the spacing. So you can multiply the spacing to make it twice as distant in the lattice between lattice points. And you can redo this solution and look at what comes out. Okay, so now you can see for that same epsilon range, the difference in epsilon is going to be much closer. And so it's a way for you to kind of explore how the potential energy and the spacing can affect your energy band diagram for a simple 1D solution. And to give you an idea on how you can do that, you want to be able to manipulate this energy band data. Okay, so say you wanted to find the band gap. So first you want to define, let's assume that this second band is the valence band and the third band is the conduction band. Okay, so let's define a conduction band and a valence band. And we're going to say it's going to be equal to epsilon of, the conduction band would be the epsilon 2. So this would be 0, 1, 2, the third index. And the epsilon for the valence band would be 1. Okay, so these would be our 2 bands. And if you wanted to find a band gap, you would say take the let's look at the numpy, the conduction band minimum. So a numpy minimum of EC minus numpy maximum of EV. And this is going to be the difference in units of epsilon. By the way, I can see an issue with our y-axis here, so let's go fix that. I put an and symbol instead of a $. So let's replot this. And okay, well, what do we have here? Wow, I put all sorts of the wrong symbols here. Let's do it one more time. So look, now we have epsilon comes up from our LaTeX notation or math tech, and k in units of pi over a plus b. Okay, so this is the first Brillouin zone. It's oscillating from -1 to 1 in units of pi over a plus b. So minus pi over a plus b to pi over a plus b. So if we now look at this, we're plotting units of epsilon. So if you want to know energy, epsilon is defined as the energy over U naught, over the potential. Okay, so you can multiply this by U naught to convert this back to energy instead of epsilon. Evaluate it. And here you can see the band gap is 1.07. Okay, so you can look at the difference between here is 1.07. Now, obviously, you'd want to check that these are at the same K value, and it's a direct band gap, or if they're at different K values, it's an indirect band gap semiconductor. And you can do whatever you want. So now you can take the second derivative of one of these energy bands and find the effective mass in that band, and then change values of the potential and the spacing to see how it affects the band gap and effective mass in a simple 1D solution. Okay, so I'll post the code for the KP solution that you see here. I'm going to post this in the description, and you can download it and import it into your own file to plot it as you like and to manipulate the bands to find useful electron and hole information about these bands. Okay, so I hope you enjoyed it.